Okay, so thanks to the rest of the organizers for this conference. I'm one of them, but again, yeah. Yeah. And thanks for attending, all of you. So this talk is based on a joint recent work with Nico Brookman and Quinn Nguyen. It's Circuit-to-Hamiltonians from tensor networks and fault tolerance. I'm expecting this to be a 30-minute talk, so it's up to you how far you want to go. So one of the really powerful notions in classical computer science is that of Cook-Levin theorem. It was proved long back around in 1960s or 70s, something like that. And it roughly says that any classical computation can be mapped onto a constraint satisfaction problem, which for this audience is a classical local Hamiltonian, a local Hamiltonian in Z basis, essentially. Okay? So that I've denoted here as HCl, a classical Hamiltonian. And this mapping is very intuitive. It says that, well, if you have some gates acting on bits, so for instance, hold on, let me use here, this one. If you have a bunch of bits that go through a gate, then you can write down a classical Hamiltonian which enforces that input and output behave in a certain way. So if this gate was, for instance, doing some operation on these two bits and these two output bits were out, then you put 4 bits for each wire, and you put a constraint saying that these 2 bits should be equal to some function of these 2 bits. And that's it. So in this manner, in this local manner, you take any computation in the classical world, and you write down, you put a bunch of classical variables, bits, and put constraints on them, and that gives you a Hamiltonian. And the nice property is that the answer to the computation gets encoded in the constraint satisfaction. That's the key thing. So this simple observation was really profound, and it's the foundation of the theory of NP completeness, which is that constraint satisfaction problems are as hard as classical computation in general. And people believe that classical computation is very hard. And it has a lot of implications. Well, I mean, again, hardness of many natural statistical mechanical problems and so on. It's all the source of that. You build from this. And so on. It's been a long time since this theorem was proved. But in a couple of decades, an even more remarkable theorem was proved, which was the PCP theorem, where PCP don't stand for any drug. They're a mathematical theorem. And the theorem says that, well, you can improve upon this encoding and encode the computation in a manner that not just the ground state of this classical Hamiltonian, but any low energy state of this classical Hamiltonian encodes the answer to your computation. Okay? So this theorem improves upon the previous Cook-Levin theorem in the sense that the Cook-Levin theorem says that, look, only the ground state encodes the answer, but this says that anything in the low energy encodes the answer. Okay. So now, fast forward to a couple of years later, Kitaev proved, using some ideas from Feynman's earlier paper, the quantum analog of Cook-Levin theorem. And the proof, again, the statement is as follows, that take any quantum computation, and this quantum computation can be mapped onto a local Hamiltonian, which has now x, z, x, and y basis, potentially. So you start with any computation, and you can write down a Hamiltonian, so that the same philosophy holds, which is that the ground state still encodes the answer to the computation. Okay? In fact, the ground state that was written down by Kitaev in this, this FK stands for Feynman-Kitaev Hamiltonian. The ground state, it's a superposition over partial computations of this quantum process, this quantum circuit. So here T is a time register, and you start with some input state psi, and when small t equals capital T, that's when the computation has finished. But in the process, this whole ground state also encodes some partial things of this whole. And in fact, what was shown by Kitaev is that not just the ground state, any quantum state whose energy, I'll be using the term energy density, just the energy divided by number of particles in the usual way. Any quantum state with energy density smaller than 1 over m cubed, where m is the number of terms in the Hamiltonian, or even maybe m is pretty much the same as t there, any low energy state also encodes the answer to this computation. Okay? And in fact, this is proven via showing that the spectral gap of this Hamiltonian is this number. So if a state has energy less than that number, then that state has to be close to the ground state, and that's about it. Okay? That's how one proves this. So why is this theorem important? First of all, it's far from obvious that this could even have been possible. I mean, notice how Cook-Levin theorem was proved. It was proven by interpreting, you take computation step by step and then just you put constraints. But in quantum case, there can be entanglement across the computation. Then how do you even enforce this kind of constraint? So it was a major insight, and in fact, from my point of view, maybe many of you agree or disagree, this really is a bridge from quantum computing to condensed matter physics. It sort of connects the two fields in a very strong way, this theorem. And after that, once you have this Hamiltonian, you can then go ahead and make it more physical by doing perturbation gadgets and so on, which has been really, really active area of research for a very long time. Okay? And it has a lot of implications like proving that adiabatic quantum computation is universal, and there's a lot of results that follow from this construction. So in a technical term, this construction shows that the local Hamiltonian problem, which is the problem of estimating the ground energy of a given Hamiltonian to some accuracy, that problem is as hard as doing quantum computation, essentially. Okay, that's what the term QMA means. So it turns out that so far we still don't know how to prove the quantum analog of the PCB theorem, as John Wright mentioned earlier today, which is one of the big open questions in quantum complexity theory. And the question basically is asking you, well, given any quantum computation, can you encode it to a Hamiltonian in a robust manner? Which means that not just the ground state or very low energy states as in here, but any quantum state with energy density less than a constant has the answer to your computation. How do you do that kind of encoding? And it has been a very difficult question for a very long time. So one consequence of PCB theorem would be, quantum PCB theorem would be, for instance, that the Gibbs state at some temperature, like a constant temperature, very hot Gibbs state, would also have the answer to the quantum computation, which seems pretty cool. Yeah. All right. So what's the challenge in this conjecture? The challenge is that, well, the Feynman-Kitaev Hamiltonian is very fragile. You can easily find states in the low energy regime of the Hamiltonian which have nothing to do with computation. They don't have any information about which computation that you started with. So that's the issue. So how do you really make it less fragile? But it has been the only way to go from circuits to Hamiltonians, quantum circuits to Hamiltonians. So that has been a challenge. So our goal today will be to talk about a new mapping from circuits to Hamiltonians. And this mapping, it's not based on the original clock framework of Feynman-Kitaev. It's based on tensor networks, and somehow fault tolerance naturally emerges as a need in this mapping. And I'll tell you about some applications like, we'll see, some applications like contracting tensor networks and some connections between QPCP and fault tolerance, and also maybe some speculations about compressing quantum computation. We'll get to that. But let me tell you also that this really, we are at an early stage of understanding this particular, this kind of mapping. So for those who have been in the field for, for a long time, just a quick, I want to lower the expectations by saying that, look, first of all, you may wonder, well, does this mapping recover the QMA hardness of local Hamiltonian problem as it does for Feynman-Kitaev? Well, so far we can only get it to some factors, and our proof is way more complex. That's how it is, but I'll tell you some ways to recover this, and those are some open questions that I'll talk about. And do the low energy states encode the computation in our context? In some way, and as I mentioned, they will require fault tolerance to be inbuilt in the process. Okay? So that's roughly my plan. Oh yeah, there's some, I'll tell you what prior work is, but any questions so far? As to, okay. Okay, all right.
One question, so when you say fragile Hamiltonian, what do you really mean by that?
Fragile, yes. Uh, I mean this precise statement, which is that, well, I'll make it more precise later, but in the Feynman-Kitaev Hamiltonian, ground state and very low energy states have the answer to the computation, so that's great. But you can go a little bit above the ground energy, and you see that there's no answer anymore. There are very simple low energy states which are totally, which have nothing to do with the original circuit that you started with.
So the gap is small to these states.
Yeah, so the gap to these states is small. Yeah, that's the way to put it. Yeah, exactly. So you want to live in a nice space where you always have answer to the computation, and that space is not as big as you'd want. In fact, this also happens in the original Cook-Levin theorem, but then PCB theorem manages to be much more robust, and the goal would be to hit that bar, which is very high. So yeah. All right. There have been some prior works in thinking about. Oh yeah, yes.
So, is there any guiding principle for finding these low energy states?
Yes. There is a very simple state you can write down, which is.
Except for the ground state.
Sorry.
Except for the ground state.
Right. If you already know about Feynman-Kitaev Hamiltonian, then it's just if you write down the state which is at time 0, tensor something random on the other states, other qubits, then that's just the low energy state, and that has no information about computation. Yeah, but I'll say more about it briefly. Yeah, later on. Yeah. All right. So in the past, there have been these indications that indeed somehow circuit-to-Hamiltonian and fault tolerance are related. So there was a very nice work of Bacon, Flemia, Harrow, and Shi 6 years ago, which showed how to map Clifford circuits into subsystem codes, and in the construction, really fault tolerance was important. Aharonov and Irani recently used fault tolerance in Turing machines in classical computation for some translation invariant versions of Cook-Levin theorem, and also building upon some works that Toby has in the past, I think. Many years ago, Zagadian, Gal, Anagal, and Mario Zagadis observed that classical PCB theorem follows from something we'll talk about a lot, which is the adversarial fault tolerance. So there are some connections of this kind. Okay. All right. So here's what. Let me just move forward by first setting up our notations so that we are all on the same page in terms of what you see. So Hamiltonian for me is a sum of local terms, usually m terms, and each local term hi will be some matrix between 0 and identity, and this hi acts on a few qubits. So I'm thinking of local Hamiltonian very broadly, not in terms of geometric locality, like I'm not thinking of 2D, 3D world. Maybe I'm thinking of much higher dimensional, kind of more connected lattice. But whatever I'm thinking about, almost always each Hamiltonian term acts on a few qubits. That's always the case. All right?
So few is defined compared to the system size?
Few is like constant, like 3, 4. Yeah. Even log the system size is often fine. But few usually just means something very small. Yeah. Energy density, as I mentioned, is energy with respect to the Hamiltonian divided by the number of terms, which often is the same as the number of particles up to some constants. But here's the number of terms. So whenever I talk about epsilon energy density states, I will say states with energy density at most epsilon. There is another notion that I will need, rather unfortunately. I wish we didn't have it, but we have it. So we'll have to carry along this weight. I'll talk about epsilon combinatorial states. These are more classical kind of low energy states. They're a subset of these states. And these are the states which only violate at most epsilon fraction of terms. So these are states for the number of local terms for which this state is in the ground space of those terms is quite a lot. So the number of terms which this state doesn't satisfy will be at most epsilon fraction of total. Okay? So, we'll have to kind of stick with this definition for a while, and it's work in progress to not show this definition in the talk anymore. But we'll need it for now. Okay, so I'm going to be very brutal in the next slide. I'm going to just throw on you all our theorems very unkindly, and the reason is that the slide after that is much more simple, and then it's sort of. I just want to put this aside so that those who know this area well, they kind of know what to expect, and then I'll give a more high-level overview of how our construction works. Okay? So this slide is basically about essentially about comparing Feynman-Kitaev construction and our construction. And for this, I will take a quantum circuit C on n qubits and depth d. Okay? So in the Feynman-Kitaev case, the ground state is, as I mentioned, is a history state. It's a superposition over partial computations of the circuit. In our case, as I will describe in the next page, the ground state is a tensor network which encodes a noisy version of the circuit with IID noise per wire. Okay, that's how it will look like. You'll see now in the next slide. In the Feynman-Kitaev case, as I mentioned, every state with energy density 1 over number of gates cubed, all those states encode the computation because they're close to the ground state, because spectral gap is this number. What we can show here is that all the states, all the combinatorial states with energy density 1 over depth, so here number of qubits doesn't appear, they encode a noisy version of the circuit with adversarial noise. And adversarial noise basically means that someone can corrupt a small fraction of qubits at every location. And in fact, our hope has been to remove the word combinatorial from here and have all low energy states. But we have much weaker bound right now. We have only exponentially small in depth bound for states, for low energy states with the same property. And in fact, what we're working on right now is trying to improve this to 1 over poly in depth. And that's one of the things that's work in progress. And these states, their spectral gap is, this Hamiltonian, its spectral gap is roughly exponentially small in the depth divided by the number of qubits, poly in the number of qubits. So its gap is pretty bad. So what's nice is that this statement holds despite the fact that the gap of this Hamiltonian is very, very small. And it's almost, you would never use this Hamiltonian for things that you use this Hamiltonian for when it comes to gap, using the gap. Okay? So that's one thing. And next thing is that, well, as I mentioned, Feynman-Kitaev Hamiltonian is very fragile. And indeed, there exists a 1 over nd energy density combinatorial state, which has no information about the computation. It's basically the state, for instance, at time 0. That doesn't even propagate. And in this case, this statement is tight over here, and there is a 1 over d energy combinatorial state that has no information about the computation. So in this case, the computation is encoded up to 1 over depth energy density in the combinatorial case. Okay?
Can I just quickly so
yes.
The epsilon combinatorial state definition, this seems to require that at least a large part of the Hamiltonian is frustration-free to make sense.
So this Hamiltonian is totally frustration-free.
It's only frustration-free.
Yeah, exactly. So the ground energy is 0. Yeah. Right. Okay? More questions about this? Okay. So that's roughly what we can show. So things on the right are what we show, and things on the left are what is known for the Feynman-Kitaev Hamiltonian. And now I can tell you about the construction of this Hamiltonian and how do we really go ahead and do it. So imagine a quantum circuit that starts from all zeros and applies a bunch of gates. And for the moment, I'm going to assume a very simple quantum circuit which acts on 1 qubit only. Just start with 0 and apply single qubit gates on that qubit. So it's been known for a long, long time, since the birth of quantum teleportation, more or less, that any such computation can be encoded in a tensor network using teleportation. And here's the way to do it. Some notations, imagine we'll view all these lines with 2 legs as the EPR pair, 0, 0 plus 1, 1, and this red box as just the quantum, the density matrix for that EPR pair. And whenever I have this thing with a unitary, then I'm applying a unitary on this 0, 0 plus 1, 1. Okay? So some notation. So a quantum state of this form can always be encoded in this manner. Well, start with 0 and prepare a whole bunch of EPR pairs with unitaries there, and then just project each of these pairs with another EPR. So what happens is that you just have a series of teleportations, and the teleportations that don't have any correction. So you're basically post-selecting on a series of teleportations that aren't correct. And once you do that, what you see is that in the end, you get out the quantum state psi. That's over here. So that's what would happen. If you did not do any correction and you just kept doing teleportation, and let's say there was no correction ever, if you post-selected on always getting the identity answer, you'd end up having this property. So this is fine. This, in fact, is one of the. In fact, it's also the idea behind measurement-based quantum computing, which is just the innovation in MBQC is that this is independent of the circuit. Well, the measurements depend on the circuit, but here it's the other way around. Here the state depends on the circuit, but the measurements are independent of the circuit. Like those measurements are all very simple. So this picture has been around for a long time in encoding quantum computation into tensor networks. So this over here is a sorry. This over here is a tensor network, essentially, if you just modify it a little bit. So there are two issues with this particular object. First thing is that, this object is not the ground state of any local Hamiltonian, which I'll not explain right now, but it's not too hard to convince yourself. Second thing is that this object leads to a class of tensor networks which are too powerful, and they capture something that goes much beyond quantum computation. They capture quantum computation with arbitrary post-selection. That means you can post-select on outcomes that would almost never show up. Like outcomes with exponentially small probability can be post-selected here. So these objects are post-BQP, and they were shown to be, I think, maybe complete for this class long back. So it almost feels like you cannot use these two problems prevent you from using this as a way to encode quantum computation into ground states of any Hamiltonian. But the way to fix this issue is to just use the notion of injectivity, which is, well, if your map is not invertible, just make it invertible by adding some noise. So what I can do is that I can then define a version of these projectors as a noisy version of these projectors, where what I do is that I just take the original EPR and I add delta times some noise, which is x plus y plus z EPRs. And this is the same as identity minus EPR. So once I do that, I end up getting an invertible map, and I can just put it on the, so I can replace from this picture, I can replace all of these red boxes with these blue boxes. And what I get out is basically a new quantum state, which is now a state on all these qubits. And this quantum state is a injective MPS in one dimension. Okay? But now, what has this done to me? First of all, the claim is that what's out here is not the original quantum state anymore. What's out here is a noisy version of this quantum state. And indeed, what you can see here is that, the 0 is now not going through the original U1, U2 anymore. It's going through a noise from these XYZ terms, and then U1, noise, U2, and so on. So what happens is that, what you can show very quickly, in fact, is that, the quantum state that's out here is a noisy version of, imagine you start with 0 and apply a depolarizing noise, and then U1, depolarizing noise, and then U2, and so on. And that's what you get as the output here. So that's one thing. Because this is an injective tensor network, it has a parent Hamiltonian, and it's basically as simple as invert these maps and then project onto these things. That's your Hamiltonian, basically. So what happens is that you are able to write down a quantum state, which is the ground state of a parent Hamiltonian. That's good. And you avoid this post-selection issue because noise prevents you from post-selecting. If noise is constant, you can't post-select beyond a constant probability event. So you can't do post-BQP. You are stuck with BQP, or also maybe QMA. So that's the construction. So what we do is that in general, we take a quantum circuit, maybe in 2D, 3D, doesn't matter which dimension. We imagine teleporting quantum circuit gate by gate, and we replace each teleportation operation with this noisy teleportation. And what we get is a noisy version of the original circuit. And of course, we don't use that circuit. We use the fault-tolerant version of the circuit instead, which requires fresh ancillary, which is easy to do, and measurement, which is also easy to do. So what we do is that if you want to encode a quantum circuit C into this kind of ground state, we first convert the circuit into a fault-tolerant version of it, and then we encode it into the ground state using this map, this kind of transformation. Okay, any questions?
Yeah, I have one. So
yes.
The picture which you had before
Yeah.
I mean, that is, without the delta, that is just essentially the composition of channels, right?
Yes. Yes.
And so now you're just adding some noise in the composition formula. Is that the right interpretation?
Yeah. So these are all basically, in some sense, these are all choice states of the depolarizing channel. These are all the blue boxes.
Yeah, noise channel.
Exactly. Yeah, exactly. So that's what's happening. So it's invertible, so you're fine. So, all right. So what we did is just yes.
Is there any condition on how big the noise has to be?
At this stage, it's totally flexible. It shouldn't be 1/3, I guess, because then it's totally noisy. It shouldn't be too high. Then nothing can be done. It shouldn't be too low. If it's too low, then you're basically back to this setup. You don't want that. So somewhere in between. So all of our theorems are about always have some play with delta changes a little bit here and there. So yeah.
Can you say one more word why you can avoid post-selection?
So imagine you wanted to post-select on this location, let's say. So post-selection requires you to apply a projector like 0. But what we're having is 0 plus delta identity minus 0. So if an event had probability to the minus n, this post-selection would only catch that with probability to the minus n minus delta. That's 0. So you cannot post-select. So it's not post-BQP anymore. Yeah. So yeah, that's the reason why you avoid the post-BQP barrier. Yes.
Describe the example as like this circuit on a single qubit.
Oh, sorry, what's up?
You described the example when you're presenting it as being on a single qubit. Of
Yeah.
course, you want to do it on multiple qubits. Does this mean you get 2D or higher?
Yeah. So imagine you start with qubits, and instead of this EPR with single qubit, you add EPR. Can I write on this? Maybe not. So you put EPR here with some gates, like all the.
So do you get a PEPS instead of an MPS?
You get a PEPS, yeah.
Okay.
Basically, you get a PEPS, yeah. Here we go.
Do you need any adaptivity when you run fault tolerance?
Adaptivity, yes. So you can do measurements, and what you can do is that measurement is very simple. So you can imagine doing a unitary, and then it's easy to trace out qubits in this picture by just setting delta to be 1. So that qubit never propagates forward, So you can do adaptivity in the sense that you can do a measurement unitarily, record the answer in 2 qubits. 1 qubit is thrown away in a simple way. The other qubit holds the outcome, and the outcome you can control on that, and then you can just do the rest of the circuit. So you have this. Here is where the computation is. This is the bulk of the computation. If you trace out the bulk, you just get essentially a noisy version of computation with all the adaptivity included and everything. Everything part of it. Okay. Yes.
This question might be a bit naive. So why did you start off with using the teleportation to do this construction? Was it to generalize the problem?
So I should have said more about that here. So let's ask a slightly weaker question, which is, well, how do I encode quantum computation into quantum states? Instead of so we are thinking about encoding quantum computation into Hamiltonian. But let's just ask, how do I encode quantum computation into a quantum state? As simple as that. So one way is to do it via Feynman-Kitaev Hamiltonian, which is via history state. Another way is to just write down this quantum state. Write down this quantum state, which is a valid quantum state encoding the computation. Of course, this is the same as this quantum state. But the nice thing is this is a tensor network. It's sort of, so this mapping has been there for a long time. I mean, this mapping basically what it does is that it tells you that a quantum computation looks complex, but it can be mapped into something as physical as a tensor network. And this is one way to encode quantum computation into something simple like a PEPS or
Yeah, I guess my question was like, why specifically teleportation to encode it into a tensor network? Because it looks like to make it work, you're doing a lot more work.
Well, this is exactly what happens in measurement-based quantum computing as well, right? Measurement-based quantum computing is basically single qubit teleportation. And if you just do it, you start with a tensor network and just do measurements, and you're essentially encoding computation into a tensor network in the process. One way to think about it is, we have this thing called quantum computation, which is very complex, and we have a class of states which we know are very simple, which are tensor networks. This is a very simple way to encode from here to here. As to why this should be done, I'm not sure. There could be some other way to do it as well. So I don't think I have a clear answer to your question, as in why this should be done in particular. Yes.
You get injectivity for any positive delta, right?
Yes. Yes.
So I guess you need delta bigger than 1/2 to the n to avoid post BQP.
Right.
Where do you see that what's going to break down if delta is less than positive but less than 1/2 to the n?
Oh, so as you'll see, in fact, quick note is that if delta was 1 over n square, then this noise is useless. It's pretty much doing the original computation with some tiny,
Sure.
So let's just say delta was like 1 over n square even. In that
It would
case,
still be, you get injectivity still then.
you still get
Still have a
injectivity.
perhaps.
You get injectivity, but our soundness really depends on delta. We'll get to that. Actually, I may not get to that, sorry. So it might be the soundness, I think, the combinatorial soundness holds on, in fact, I think it's like a poly delta as well there. So delta can't be too small, basically. Yeah. So think of these as, a series of noisy teleportations happening. And each teleportation is happening with error delta. So if delta is too small, it's all good, but then somehow the Hamiltonian is more fragile because, it's basically like original computation, more or less. Yeah. Okay. All right, so given all that, let me tell you about applications. Oh, wait, am I too fast or no? I think it's fine. Yeah. So a series of applications. So first of all, what we can recover is, somewhat embarrassingly, we recover the fact that local Hamiltonian problem with n to the minus log n soundness is QMA-hard. 20 years ago, Kitaev already showed how to get n to the minus 3 soundness, and with a lot of hard work, we get n to the minus log n. So not something we are proud of, but there's something useful going on. So let me just go over that. So it's bigger than Kitaev. I'm glad no one has tomatoes here. So that's very good. But it's still quite maybe useful to say a few words about this result, which is, well, what we need here is, well, we use fault tolerance, of course, but we really need fault tolerance with some of the more recent fault tolerant results, regarding QLDPC codes and stuff. We really need that machinery to achieve this. Basically, we want to get fault tolerance with small depth overhead to get this result. So, and where does that come from? Because it turns out that the fact that in our construction the soundness depends on 1 over depth instead of 1 over the size of the circuit is really crucial. Because in quantum computation, sometimes when you have help from some prover, you can take any quantum computation on n qubits of depth d and convert that with the help of a prover, that's the class QMA, into a quantum computation of depth log n, roughly. So if depth is log n and our soundness is like exponentially small in depth, like e to the minus d log d, you expect that this kind of result would be recoverable. But of course, in the process, you need some fault tolerance, and that's what happens in this theorem. But we also know that if there was a quantum fault tolerance scheme, if there was a scheme to convert any circuit into a fault tolerant one, in which the depth overhead was only a constant, which is in fact a current active area of research in this field. In that case, you would be able to recover the soundness of Kitaev. So that's one thing. Second thing is a possible link between quantum PCB with 1 over polylog soundness and adversarial fault tolerance. And as I mentioned, the depth that you need for QMA is at most log n. So we're really thinking of log depth quantum computation as far as quantum PCB is concerned. So given that, our results indicate, and in fact show it in the combinatorial case, but not for the full case, that getting 1 over polylog version of quantum PCB is possible with adversarial fault tolerance. So that's something which still work in progress into trying to improve the combinatorial part soundness to the full soundness. Okay, and one of the consequences of the result directly is that we get BQP hardness of contracting tensor networks. So if you have a injective tensor network, it encodes the computation. So you just get directly BQP hardness. And also, there is a very nice question out there. It's been around in the field for a long time, which is that, well, if you have any quantum computation where you don't have help from a prover, or even you don't have any prover to work with, can you take any quantum computation and shorten the depth to polylog or log or something? So that question is open, but the fact that you can encode this into an injective tensor network suggests that maybe sometimes you can replace BQP circuits with small circuits, because there are ways to adiabatically prepare injective tensor networks if you're lucky, if the gaps work out. So that could be used in shortening the depth of BQP circuits. Finally, I guess it's not so relevant, but this kind of tells you that you can encode quantum computation into these tensor networks, and these are hard Hamiltonians with area log ground states. In 1D, the picture is very different, where you have QMA-hard Hamiltonians, which always have volume log ground state. So okay, so in conclusion, it's a new mapping from circuits to Hamiltonians, and the soundness looks very different from what's there in Feynman-Kitaev, so it's something which we are still exploring. And it requires fault tolerance inherently as in its build-up. And this picture is often has shown up in the past in classical PCP, also in the recent NLTS theorem with Chinmay and Nico, where you get hardness results from error correction. And that's what we see here as well. In fact, this construction is inspired by one of the NLTS constructions. And main open question that we have, which is that, well, can we get one or poly depth soundness with adversarial error? And can we get QMA hardness with the usual soundness? And that requires, as far as we know, it requires fault tolerance with constant depth overhead. So that's about it. Thanks.